Bonjour à tous.
Good morning, everyone. I called my speech Indoor Culture, Applications in Ornamental Horticulture. I'll define indoor culture, its pros and cons, and then I will give you an example, an implementation in ornamental horticulture, which is the production of young plants. What is indoor culture? It is a production system in a closed environment, totally closed, with a fully controlled environment. Climate, all growth factors, that's what we're looking into right now, light, temperature, CO2 concentration, hygrometry. And what's specific in this system is that we work in several floors, or shelves, if you will. So it's vertical farm, indoor vertical farm. In that production system, what do we produce? Mainly low-volume plants, leaf vegetables like lettuce, rocket, some cabbage, aromatic plants like basil, or strawberries, what you can see in the bottom picture, indoor strawberry production. Those systems were developed especially in Asia and in North America. Why? In Asia, well, we can take the example of Japan. It's a country that strongly depends on food import. It also has an aging agricultural population, and it had to face a series of health scandals. And in North America, we have a large urban population that really eat a lot of local vegetables and fruits all year long. So in those regions of the world, it promoted indoor vertical farms. So the pros and cons. What are the advantages? Well, you got it. By controlling growth, you can increase yield significantly. For basil, 50 kilograms per square meter per year. Second advantage, very low surface required thanks to the shelf system. So in urban areas with land pressure, it helps. And it's enough suggestion to refurbish industrial buildings. It has low input consumption, water, fertilizing, phytosanitary products. It's not affected by climate change in terms of drought, floods, etc. And last advantage, because the production areas are where the consumers are, there is a significant reduction in transportation cost. But one of the main drawbacks is it consumes a lot of energy, and given the current context, it is a major issue. So energy consumption for the lighting and also for the air conditioning of the building. And second drawback is that the range of vegetables that you can grow is limited, only low-volume plants. So all the leaf vegetables that I told about. This production system got developed thanks to one specific technology, which is pretty recent in the history of horticulture. It's the LED lighting. So this has been developed for horticulture for the past few years, and it has replaced the sodium vapor lighting. So advantages of LED, light emitting diodes. It enables us to control the photo phase, the light intensity, and also the light spectrum, which was not possible with the previous lamps because they had a fixed spectrum. Other advantages of this kind of lighting is the Sorry, I said low efficiency, but I wrote down high efficiency. The conversion of electrical energy in photosynthetic photons, that is to say, useful light for the plant, is way higher with LEDs compared with sodium vapor lamps. I read in the literature that for blue LEDs it was 93% of efficiency, red LEDs 81, white LEDs 66%. But discussing with suppliers of lightings, they tell me it's overall 75% no matter the color of the spectrum. But still compared with sodium vapor, it's about 40% better, which is really good. Which means that it produces less heat. So they can be set closer to the plant without burning them. So it increases the height to which you can produce. You can go closer to the lamps. So the LED lighting, it is interesting, as I said, because you can control the light spectrum. Therefore, you control two important processes. On the one hand, photosynthesis, with only the wavelength that it requires, blue and light red, that are captured by chlorophyll, and morphogenesis, with blue, LED right, but also dark red spectrums. Given the wavelength, there will be a response by the morphology development of the plant. So we can control the development and the morphology of the plant. Now, let's look into an example for ornamental horticulture. I chose the production of young plants because it's a good example to illustrate this kind of ornamental culture. Why? Because for ornamental plants, we produce young plants between December and February in greenhouses, sheltered growth, and it is not favorable to growth because in our region we don't have enough light in wintertime. So we're using this indoor culture system to get rid of the season limitation by controlling the climate and the growth system. And second advantage is that we can also control the quality of light. On the one hand, to promote photosynthesis, but also to control the development of the plant, because what we are looking for in terms of quality for young plants in ornaments is to have young plants that have a well-developed root system and also that have a lot of branches and compact aerial aspect. So we'll use photosynthesis and photomorphosis by playing on the light levels to obtain what we're looking for. So that's what we looked for, the best light solutions to reach this quality objective with our young plants. This was worked on through the CASDAR project, CASDAR IRRADIANCE project, in collaboration with ASTREDHOR, that I led. And I'm going to show you the main results of this trial. We tested several light solutions. On the graph, you can see the light spectrums that we have tested. Here you see the wavelength horizontally and vertically the intensity of the wavelength. So in black we tested white LEDs only, with a peak in blue here. Then blue and red, and then white and dark red over there. Second solution we tried is that a mix of white and light red mix. So we can see this spectrum here, and there's a peak in blue, of course, but more important in light red with a higher ratio, 23.2. And the last trial a mix between light red and dark red. And once again, we had a peak in light red, but an extra peak in the dark red too, with a ratio between both colors of 7.5. So we started studying the effect of this light on the root system. We worked in a closed environment with these conditions: 24 degrees Celsius per day, 22 per night, hygrometry 80%. In the cutting phase, we had 16 hours of photophase, and we compared it with 22 degrees in the day, 18 degrees in the night, and hygrometry 80% and photophase 16 hours. So we studied that on rose trees, because this is what we work on. And we worked on one variety first. What I forgot to say is that most of these, all of these light spectrums, the light intensity was the same, only the quality of light varied, not the intensity. Results for the root system. We assessed all these modalities on two variables: the development of the root system, and here, the lengthening of roots. So the black bar is the greenhouse modality, and the red bars are about the two different solutions of reds that I told you about. As expected, we observed a strong positive effect on the closed environment compared with the greenhouse. And the various modalities are much stronger in the closed environment compared with traditional greenhouse. We can see that there are way more roots on the one with the red lights. Another interesting factor for the length of roots, we observed differences in favor of the closed climate environment, but also variations between the light quality. So especially dark red was particularly efficient. So a second advantage that we could observe in our trial. So we looked further into all that, working on the aerial system. We want a plant that has strong roots, but also have a lot of branches and compact leafage. So same light modalities, but testing in climate control indoor system with 20 degrees per day, 18 degrees per night, 70 degrees hygrometry, and we worked on two rose varieties. They were not chosen randomly. One was known to have a high plasticity regarding the environment, and the other one was very stable, whatever the environment. So we could compare. The results we got. Firstly, we observed longer stems. So that's one of the plasticity aspects we wanted to look at. So you have the variety knockout and zoopharia that was also used for the previous studies for the roots. For zoopharia, we can see that the dark red boosted light promoted longer stems. We kind of expected that result. Why? Because by reducing the ratio dark red, light red, it avoids the plants to avoid shadow. The plant wants to avoid shadow, and so promotes stem growth. And the knockout variety did not respond to the quality of light. No matter what the solution of light we chose, no difference in terms of stem. So we realized that, yes, the genotype does react to light quality. How about the number of branches? Same thing. For zoopharia, there's an increase in branch production with darker red light. It was not expected because If you have longer stems in natural conditions with a shadow avoidance, you usually have less branches. So we wondered what happened. It promoted longer stem and more branches. For knockout, there no response to light quality. So this is what plants looked like after 1.5 months of growth in climate control indoor farm. So response to light, white, light red, and white, light red, dark red. You can see a better development of branches and leaves for the fairy. So we wondered, why such a response? Especially for branches, it wasn't clear what happened. So we looked into the ecophysiological, ecochemical physiology of the plant, and what happened for the fairy. More red, dark red, caused two things. Longer stem, so longer internode length, so better penetration of the light through the canopy, so better photosynthesis. So that's an advantage that is very important. More photosynthesis, so more biomass, so more branches. And second effect that we can see here is that dark red increases the net rate of photosynthesis. So photosynthetic activity is increased by nearly 10% here. So if you bring together both phenomena, more photosynthesis as a whole and more efficient photosynthesis, so faster growth. So the growth is accelerated. That's really what's happening here. For knockouts that did not respond to the light, what happened? Looking into it, we highlighted that for knockout, there was abscisic acid production. What is this acid? It's a inhibiting hormone. It has an inhibitor effect. And so in the stems, it inhibited the hormones that are promoting longer stems. So it didn't increase the positive effect of dark red, because they're not longer internode space. Same thing with leaf production. What happened? Increase of the abscisic acid, more concentrated, and it probably inhibited the photosynthesis gene expression. So no stimulation of the dark red for morphogenesis, longer stems, and for photosynthesis, growth of the leaves. So cancelled effect, no response. Now, as I said, we have a lot of branches, but scarce leaves. So what can we do to have more compact leaf production? So we added a bit more blue light. Why blue light? Because it is known to promote compact leaf production by reducing the auxin that promotes longer stems. So that's what we tried. To try and make it clear, you have cultivated plant with our solution with darker red. And here we added a bit of blue light with its compacting effect. And so we reduced the stem by minus 47%. So it's quite significant. And you can see on the picture, here it's longer. And compared with greenhouse culture, you can see that the plants are as compact with more branches, an extra 78% of number of branches. So we had growth and leaf growth. So closed environment enables us to control growth factors to mimic spring. So it's better than greenhouse, and it was expected. But what was not expected and interesting is that by changing the quality of light, adding darker red, we boosted photosynthesis directly and indirectly. We produced more biomass, we accelerated growth with longer stems. With more blue, we made them longer and more compact. But dark red, the quality of light in general, interacts with genotype. So for producers, they need to take into account this genotypic aspect and choose the genetics depending on what they're looking for in their production system. That led us to think about the development of this technology with our horticulture partners. In the Casdar QUALILED project with Oscar Stapel from Steppe Bretagne, Oscar developed a production unit that I called low cost but high tech. He used a cultivation tent, which is usually used for cannabis. So it's something that you can find easily in Northern Europe. And he used it with cultivation shelves that are lit. Each shelf is irrigated and lit. They're also heated with an interaction and extraction of air. So these are cultivation of young basil plants. So they compared with greenhouse cultivation and this module for cultivation, if you will. The cost, because everyone wants to know the cost. When he started this, Oscar, when he thought about this small module, what cost the most was the buying of the irrigated and lit shelves. It was 8,000 euros. So the rest is not much in comparison. And since, with our agro suppliers, we have seen the emergence of already prepared shelves that are way more affordable, divided by 10 in terms of cost. So we can have about less than 800 euros before taxes, these rolling shelves that are already lit. So the cost has been reduced strongly. Now it's about 1,500 euros for the module. And we took it further. We actually tried to look into, because the light is what's missing through the winter, while putting our rolling shelves within the greenhouse, could we not have the same result? So we also tried to have a very simple system to put the lit rolling shelves in the greenhouse. The advantage is that you can have bigger surfaces. The horticultural producer does not need to invest in closed environments. And thanks to the verticality, they reduce the heat because the volume of greenhouse that needs to be heated is divided by 4. And thanks to the reduction of heating, you can pay for the lighting. Because the light is very close, thanks to the LED technology, we can have the light very close to the plants, so more savings. And to conclude, an example of such production for the MAP sector. Here I took the essential oil production, same for lemon balm, same thing than for our roses. I measured the rate of citronellol, which is the main component we're looking for in lemon balm essential oil. So here you've got what represents the greenhouse. The blue bar is the greenhouse, and the other ones are different light solutions in closed environments. So once again, the climate-controlled indoor is much more efficient than the greenhouse, more biomass and higher rate of citronellol. And the coupling blue-red light with closed controlled environment increases by 50% the biomass and the level of citronellol. So it's really, really efficient. So to conclude, this production system indoor, to me, is really interesting for products with strong added value. I think essential oil is one of these strong added value, high added value products. So it's very interesting for such production. Thank you for your attention.